Okay, so I mentioned the other time that I was actually going to make a separate video for this. So for the remainder of the course of the topic we started, multivariate regression, we stop here on Wednesday, and of course I said I was going to make a video. So this is expectation and covariance of residuals. Of course, we'll be working on multivariate linear regression. And what we want to do here is we want to be able to look at the expected value of residual, being the average of residual. Of course, we know from assumptions that that should be zero. So take a look at that. This is the actual response, and this is predicted response. And of course, this can be factorized as this, where each is part matrix. And if I take the expectation of all of that, the expectation we attract y. And of course, this guy I minus AH, because that depends on X variable. So it's a constant, so it's going to come out. So right now, and we know that from the model, the expected value of y in the model is xp. Okay, so if you make an attempt here, okay, if you multiply out, so identity multiplied by ASP is going to be xp, okay, minus, and that multiplied by that, I'm actually going to have h xp, okay. Now, and the art matrix the other time, the art matrix is actually the art matrix is if you can recall from what we done before, I think I show what each actually represent. 1 second, you actually just want you to to see the art matrix that we've mentioned that before. Okay, so it's right here. Okay, so this is the art matrix. So if the art matrix is X, okay, X transpose has. Just to be able to show you that we've mentioned that before, okay, then X transpose. Now, if you go down to what we're doing, okay, so if you go down to where we are at the moment, it's actually gonna make a whole lot of sense. Let me see. Okay, so it's gonna make a whole lot of sense. So if I put the whole of this guy now, if I put it here, okay, so what is it gonna be? So let's take a look at that. So if I write xb minus h, and my h is x, x transpose okay, inverse S transpose as at matrix, and I write X, B. Automatically, this guy is going to be identity. And you're just going to see that we're going to end up having XP minus XB. Okay? And that would be 0, which is why this is going to be 0. Okay. Now, we've been able to show that the expectation of that equal to 0. Now, we also need to show we need to derive the covariance. Okay, so the covariance of the variance of the vector, the transpose of the error transpose. I mean the transpose of the estimated error, that is the residual. Okay, so this guy, okay, is actually what you see here. This guy is this guy. Because we all know that our E, okay, we know that our E is this guy. Our E is I n minus identity. I mean, minus the art matrix Y. So if I find the transpose of this, it's going to be, this is going to change position. That's why you see here. Okay. Now, if you see that right now, okay, from here now, okay, the vec of Y and that, this is going to be a constant. Okay. And if that happen, okay, this can be written as I minus H multiplied by that, the vec of that. Okay. And in that case, because this guy is a constant, okay, because this guy is a constant, okay, I can, if it come out, it's going to be a square. So that very squared is trying to say this, and its transpose around here. Okay. And of course, its transpose is still going to be the same as this. The transpose of, because you know the other time I said the art matrix is symmetric. The transpose of art matrix is art matrix. So the transpose of this guy is also this guy. So that's why you have that guy now. So having this guy now, of course, you can see that this guy is actually this one. Okay. So what is a vec? Okay. What is the variance of the vec of y prime is this guy. Okay. And in the end, if you take a look at what you have, okay, you're actually going to see that what I have here, we can follow, is actually going to become that guy. Okay? You follow what we've done before. Okay, so if that is the case, okay, and the situation where we said the vec, we can make a conclusion that, okay, if the variance of the vec of the transpose of the estimated error is this, then finding the inverse of that, so we can conclude that, when you do the transpose of this guy, it's just going to change positions. That's why you have this guy here. Okay, so these two are connected. So this is the transpose of that. So this is the transpose of that. That's what I mean. Okay, now I'm actually moving now. Now, we've been able to see that the distribution of residual, because the distribution of residual is very, very required, is part of the absorption. Okay, the distribution of residual has to follow normal. So what we're trying to say here that the vec of the residual now follow normal distribution with this as the mean and this as the covariance. And of course, that of its transpose is going to be this. So the only difference between this and this is that this is the transpose of that. That's all. Then we can also talk about the covariance between two columns of that. Don't forget, this guy here is actually, it composed all residuals for the response, all the response variables under investigation. So we can look into the covariance between, any two residual. That's what this guy is trying to say. Okay, so in the summary of results, we've been able, because if you want to perform inference on the estimate of regression parameter, we expect in multivariate linear regression, we expect to see the distribution for the vec be estimator. Okay, so the distribution, for that follow normal with the mean of vec of B, and this as the covariance, as the covariance matrix. And of course, if I want to perform inference on predicted, Okay, when I say predicted Y here, I'm talking you have more than one Y, more than one response. That's a lot of response. That's why the VEC is coming in. Okay, so you know, the distribution of that, we're gonna say follow normal distribution with the VEC of XP. Of course, when we were dealing with one response variable, it was just why that follow on normal distribution. Okay, we just XB. There's not going to be a vec if the response is you have just one response variable, and of course um you know this is going to be sigma squared identity, no, sigma squared identity or whatever. So just take a look at that. Okay, so these are the distributions of the uh you know what could be characteristics of interest if your interest is on estimate of the parameter of the linear regression in multivariate setting. We know it follow normal distribution with the mean and the variance. Okay, if you want to focus on the prediction, okay, the fitted value, okay, so it follow normal distribution with that and this as the variance. And what about the error? Okay, there's the residual, okay, in multivariate. Okay, follow normal distribution with this as the mean, and of course that's as the variance. So you can see that's exactly what we stated out here. Okay, so and how do we do all of this in now? I would advise that you study that. Like the example I'm giving here now is if I'm only focusing on one response variable at a time, I'm looking at the effects of these three selected factors. And of course, this is the result. I think I showed you this yesterday. Okay, I show you all of these. And this is when I'm looking at it one at a time, looking at the response one at a time. The only condition under which I can look at the response one at a time is when I actually, there's an assumption that the response variables are independent. Okay, independent means there's no correlation. And that's why, looking at it separately would be fantastic. But if not, okay, if there's a correlation among the response variable, of course, we don't want to ignore that correlation. Of course, we're going to use multivariate linear regression in that regard. Okay, so just like the same thing that we have in multiple linear regression model with one response variable where we actually compared fitted model with, I mean, we compare reduced model with complicated model, the one I call full model with reduced model, model with few numbers of explanatory variables, and the other one with more. So we can also do the same by test hypothesis, between two competing model. And of course, one of the model, the complicated one, is actually going to have p numbers of parameters, and the reduced one is going to have a q numbers of parameters. So if I look at if I look at all the parameters together, I'm expecting it's like I'm partitioning. When I partition B into B1 and B2, okay, and I want to test that B2 equal to 0 against it is not. Okay, it's like I'm comparing saying that B2 equal to 0 will mean a reduced model. B2 not equal to 0 will be a complicated. That's exactly what we mean. Reduced model, talking about the number of, a model having a fewer numbers of parameter or fewer numbers of explanatory variables compared to the complicated, and they also need to be nested. Okay, so we actually, because the analysis that will be conducted will be analysis of the sum of square error, the unexplained variation. So, of course, in the case of multivariate analysis, it's actually going to be called the sum of square cross product error. Okay, we're going to compute that for full, we're going to compute that for reduce. The one for the full. So, if you take a look at what this guy is talking about. This is the one for full. That was why you see a P, P numbers of explanatory variable, and this is the one for reduce Q numbers of explanatory variable. Of course, we expect P to be greater than Q. Okay, so but they are nested. Okay, so reduced model is nested in complicated. So we need to be able to compute the sum of square or cross product error for each because that is what we're going to use in the analysis. Okay, so and we can actually conduct hypothesis testing on that using the likelihood ratio test. Okay, so using the likelihood ratio test, of course, if you take a look at what I have here, B1 and the entire B. Okay, the B1 and the entire B. Okay, this one has Q numbers of parameters, the model here. Okay, the model from which this likelihood was derived. And of course, B is actually P numbers of parameter. Okay, P is greater than Q, just like what I said. And at the end of the day, you're actually going to see we arrive at the ratio of two covariance, the covariance structure for the entire, for the complicated and the one for reduced and the one for complicated. So, like I said, this one we be the one where we have P numbers, and this one, the one that you have Q number. So the denominator is the complicated, and the numerator is actually the reduced. Okay. So, and also I say here the MLE of that will be unconstrained. Okay. Unconstrained means full. Okay. It means full model. Okay. The covariance for the full model, that is all constrained. Okay, I mean the covariance for the full model. Okay, but when you take a look at this one, that would be the covariance for the reduce because that is being constrained. So, and that was why in the wiki lambda, okay, here we actually having the ratio of the two covariances is going to be the covariance or the estimated covariance for the full model and the estimated covariance for the reduce. Okay. Now, if that is actually if that is taking, I'm actually gonna move right now. The test statistics, the moment you get your wiki lambda here, um, then the test that you can take the log of the wiki lambda multiply by negative v. And what is your v? The quarter, your v is what do you have here? Where you have, your N, your P, your Q. N is the number of observation, or P is the numbers of variables, explanatory variables in the full model, and Q is the numbers in the complicated. Okay, so and N, is going to be the degree of freedom, for the chi-square. Okay, just wanted to take note of that. So which means the test statistic will reject the non-hypothesis if this guy here is actually greater than that. The chi-square is going to be the critical score. That's what we're going to use. Okay, so apart from using this approach, to investigate between the reduced and complicated and the full model, where there are other tests that can be used, okay, for search, where we can use the wiki lambda, the pillar trace, Otelin, lowly trace, and the row greatest root. And if you take a look at all of that, they centered on, you know, you getting your E. Okay, we take a look at the error. Okay, and the very E here is actually this is all together. Okay, your that very E is the covariance multiplied by N. Okay, so that would be for the full model, just like what I said. Okay, that will denote, that very E here, okay, actually denote the SSP error for the full model. Okay, that's exactly what you see. Then divided by that. And what is going to be my H? Okay, so I needed to pay attention. So that very age is going to be this guy. Now in the H, this guy is the covariance structure for the reduced model. This one, the covariance structure for with the covariance structure for the full, and this is for reduce. Okay, so which means if you want to test between simple between reduced model and the full model in multivariate linear regression, of course, this is going to be your non-hypothesis, and this is going to be your alternative. Okay, your non-hypothesis actually supports reduce. Okay, your non-hypothesis actually supports reduce. Why the alternative support full? Okay. The alternative actually supports full, while this supports reduce. And of course, the wiki, if you want to go by wiki lambda, this is what you're actually going to use. So which means, and you compute E from here, which is the sum of square cross product for the error, and you compute the H from here. Okay. And of course, at the end of the day, that's going to be your wiki, the test statistics for wiki lambda. Okay, so you're actually going to see every other test they are in terms of E and H. If you take a look at all of that. Okay, now how do we do this in R? Just like what I said, if you want to compute this in R, okay, or for whether wiki or for pillar trace or whatever, how do I achieve this in R if I want to test hypothesis between a reduced model and a full model. Okay, don't forget a reduced model is a model with a few numbers of explanatory variables, and the full model is actually the one with we have more. Okay, the number of explanatory variables here is more than the one here. Okay, and like I said, these are the possible test statistics that can be used. And of course, E and H actually is from here. Okay, you compute that from the covariance structure. So, but how do we do it in R? If you want to go by the example that I gave the other time. Okay, so my Y. Okay, don't forget this particular Y here. It has a lot of response. It's vector, not just a single response. Okay, not just a single response. Okay, there's a lot in it. Okay, that's why we have the MPG, the HP. So the numbers of responses is not one. Okay, but here, if you take a look at this one, we have two explanatory variables. Okay, so let me just say precisely, the full model is this model one. Can you see? What make it a full model because we have one, two, and three. And the model two is the restricted model, is a restricted model. Okay, the restricted model because we have to explanatory variables, and of course that is nested in that. Okay, so how to do that in R? So means I need to run this guy, model one. I also need to run model two, then I'm gonna do the ANOVA. Okay, if you take a look at that now. So I'm doing the ANOVA into each model. Okay, so this one, uh, the NVMOD is actually going to be for the full one, and the NVMOD 0 is actually going to be for the reduced one. Okay, so when you take a look at what I have here, so this is the p-value of the text, the p-values for the wiki. Okay, so that is the p-value for the wiki, or whether to reject or is not or not. So the one for the pillar trace, this is a p-value. Okay, and if I want to learn how to compute or model what I show you the other time, okay, the all of these, okay, all of this guy, okay, so we have them here, so you can study that in now. Okay, you have them here. Now I'm gonna move. I'm moving to interval estimation. Of course, when we were dealing with one single response, we had a prediction, and we had an interval for a prediction, and the prediction can be individual one, and it can be average one. The average one is called the interval estimation. So we can, if we want to have an interval estimation, okay, so which means we actually want to estimate the expected value of the response for a given predictor score. We have predictor score. Okay, we have the explanatory variable, which we also want to figure out the expected value of that. So this is the predictor. This is what we're going to use. Okay, that's a predictor. That's what we're going to use. And that follow normal distribution, which with that, with this as the mean and this as the variance. And since we know the distribution, we know the mean, we know the variance, of course, we can conduct hypothesis testing about it. We can construct confidence interval about that. So this is testing hypothesis about it. And of course, we're making use of a t-squared. And of course, this is the estimator, as you can see. And this is the mean of the estimator. And this, what you have here is the standard deviation. So if you compute all of this, that will be Ottolenghi squared. And you reject H naught if the Ottolenghi square is greater than the critical score. Then for the confidence interval, this is the confidence interval. That's what you're going to use for the confidence interval. And whatever you do there, it's just going to give you, the one for the interval estimation. Now, what about predicting new observation now? If I want to estimate observed value of a response for a given predictor, we're still going to have the same, except that the variance or the standard error is not going to be the same. Okay, I can test hypothesis about it. Okay, and testing hypothesis about rate, of course, I'm going to make use of the Ottolenghi squared. Then I'll compare with this. And the constructed confidence interval evaluate, of course, the confidence interval for individual prediction, don't forget, we call it a prediction interval. Okay, so that is that. But in principle, we expect this to be wider, the one for individual to be wider, or why the one for the average to be narrower. Okay, I also said the same on the a single response. Okay, so how do we do that in R? Okay, I'm actually gonna show you how. Now, of course, if you take a look at what I have, this is when I'm focusing on MPG, okay? But what if I want to focus on more than one response variable, okay? This is it. This one is the one for when you say confidence interval, that is, I'm having that at a group level, okay? The average, okay? This is for the group level, the average. Okay, the average prediction, okay, the interval for average prediction, okay, for each of the response variable. You can see for each of the response variable, okay, for each of the response variable, if this guy is a predicted value for the MPG, this guy is going to be the interval, the lower bound and the upper bound. We're also going to have for each of the response variable Y. You can see that. So this is the one at group level, the one for the confidence interval. So you can see here, you know, when we are actually doing this, giving the values of predator. Okay, we believe there are three predator. Okay, the AM, when the AM is 1, when the carb equal to 4, and of course when the cylinder level is 6. Okay, that is what we're doing here. Okay, that is a prediction we're making across the dependent variable, the response variable. Okay, but you know what about for individual? Okay, so I just wanted to see, just like what I said, there's a difference between the one for average, prediction for average is called confidence interval, prediction for individual is called prediction interval. So we're still repeating the same. Okay, we're still repeating the same, except that in R, if you don't tell R what you're doing, like it's going to take it as a confidence. But here, if you indicate, let my interval be prediction, it's going to do prediction interval. But there's something I need you to see. Prediction interval is going to be the same for point estimate. If you take a look at this, it's the same here. You can see they are the same, but the interval estimate is not going to be the same. You can see for the prediction interval is wider, 9 point something to 32. That's wider. Okay, this is wider. Okay, if you take a look at that, it's wider. Okay, why this is narrower? I just wanted to see that. Okay, and why is it narrower? It is narrower because the standard error associated with the average is actually smaller than the standard error associated with the individual. So that is the reason. Okay, so that's what I wanted to say. Okay, so I think that is all what I got. So you can, this is revisiting for all of that for MPG, getting that for that, for this, for that. So you can actually, so right now, this is when I'm making prediction for all the levels, 4, 6, and 8. Okay, and I'm making prediction for when they equal to 0, 1, and 1, and just like I'm actually making down prediction interval and confidence interval for all of that. Okay, so that is the end of that. So the next of course on uh, Thursday we're gonna start a new topic that we'll call principal component analysis. Bye for now, everyone.